All right, so in this video, what I want to do is walk through some of the things around sensitivity analysis, and we're first going to start by looking at an optimization problem and thinking about it from a sensitivity perspective, and we're going to move on to think about it from making some connections with the Tableau and particularly with the revised simplex method. So let's start with a problem, and we'll just define a fairly simple optimization problem. So I want to optimize the objective function 3x plus y subject to some constraints, and I'm going to have a few constraints here just to make the point that I want to make. One constraint is that I'm going to have x greater than or equal to 0 and y greater than or equal to 0, right? So I'm operating in the sort of standard region for simplex. I'll have a second constraint that y has to be less than or equal to 3, a third constraint that x is less than or equal to 4, and finally the constraint that x plus y is less than or equal to 6. And if I want to just think about that graphically before I do anything with Tableau or anything with sensitivity analysis, I can see that the region that I'm interested in, if this is 3, that's 4, this is the line x equals 4, this is the line y equals 3, I also have the line x plus y equals 6, right? So my feasible region is this region in here. And if I also think about what my level curves look like, my level curves will be the curves of constant 3x plus y. So one of those level curves will correspond to 3x plus y is equal to 0. Another level curve will correspond to 3x plus y is equal to 1, 3x plus y is equal to 2, 3x plus y is equal to 3. So my level curves are these lines like so. And if I look at those level curves, it's pretty obvious initially where my optimum is going to be, right? I'm going to sort of march along here, and the last thing I'm going to hit before I completely exit the feasible region is going to be this intersection right here. So that's going to be my optimum point. Okay. All right, so with that in mind, let's do a little bit of thinking about how this problem is from a sensitivity perspective. And let's just think graphically about a couple of things. The first question is, how sensitive is this optimum to the actual objective function? So question 1. And in particular, I'd like to know how much does it matter maybe how much I change this x coefficient. Like maybe this x coefficient is what is sort of the profit that I get from one product. The y coefficient is the profit I get from some other product. So in particular, how sensitive are we to the x coefficient? Well, qualitatively, if I think about it, when I change that x coefficient, what's going to happen is I'm going to change the slope of the level curves, right? And pretty clearly, if I make that x coefficient be larger, that slope's going to get sharper, right? And I can see that for any sort of higher value of slope up to a slope of infinity, I'm still going to hit this point here, right? And in fact, when the objective function depends only on x, I'll get a vertical line here, at which point I'll intersect with this constraint, and this entire region will be an optimum. That entire line will be an optimum. But for any sort of objective function where this value is greater than 3, I'm going to intersect here. And also it's going to intersect here so long as this value is greater than 1, right? If I think about once I get to x plus an objective function of x plus y, that's going to have a slope of -1, and that slope of -1 is going to intersect this line. So long as this coefficient is greater than 1, my optimum stays the same in the same location. All right, so that's one sort of way to think about sensitivity, is that there's a sensitivity to the x coefficient. It's sort of a one-sided sensitivity. I'm only going to lose this optimum if I start to make the coefficient of x to be less than what the coefficient of y is. A second question I could ask is, how sensitive are we to things like some of the constraints? So for example, let's think about this constraint, x less than or equal to 4. what happens if this constraint changes? Maybe this is the amount of material I have available, and instead of having 4 units available, I have 5 units or 6 units or 7 units. What's going to happen? Well, if we look at graphically at this and think about it pretty clearly, if this constraint were a lot less, right, that will pull this constraint back, and say I had a constraint of x, less than or equal to 2, then my feasible region would actually be this box here, right? And my optimum would no longer occur at an intersection corresponding to the x plus y equals 6 constraint, and instead would occur at the intersection of y equals 3 and x equals 2, right? So pretty clearly, as I change that constraint, the location is going to change because my feasible region changes. By the same token, if I start to make x be bigger, right, once x gets to be bigger than 6, right, because this intersection is at x equals 6, right, then that constraint is out of the ballpark again, and I'm going to be having an optimum that will be at this point instead of at the intersection of this constraint and this constraint, right? So it's also possible as you change constraints that the location of the optimum changes because the actual intersections change. Or it changes in another way of thinking about that is that's a change in the sort of shape of the feasible region. And in particular, a change not only in the shape, but in what points are actually in the feasible region. Okay, so that's a sort of qualitative way to think about the sensitivity analysis, is that as you change your objective function, obviously what that corresponds to is changing what these level curves are, and therefore changing where you actually hit your optimum. As you change your constraints, you might actually be changing what the shape of the objective function is, of what the feasible region is, or you might even be changing which points are in the feasible region. All right, so let's try to see how much time we have here. I think we'll stop at that point with this video, because in the next video I want to get a little bit more formal and start to introduce some of the ideas that take advantage of MATLAB's power to take this sort of qualitative picture here into a more quantitative picture.